you need to start thinking about which one you want to take. There is some sort of order. This one we're doing right now, live with me, is sort of this one from 4 years ago, the last time I did it, which is material selection. I'm going to skip fracture because Dr. Belmar's done it up here in a more modern form, 2012. I will do NDE. I probably won't do welding metallurgy. In fact, I think if you look on this one, you'll find I didn't do it in 2009, but I probably did it back in 2007, which is not on there. Next semester, I might do welding metallurgy or something, a new version. I'm doing more on material selection. I am actually going to get into different metals, okay, and different materials. And so we're going to do like 8 or 9 lectures on material selection. There's this one on casting. One of these says casting somewhere.
Insert of materials processing and casting.
Yeah, right. Okay, this one right here. That one is where I prove that you'll never make structural materials by nanotechnology. And then I get into a description of casting, and I really need to get into more of the science of casting. So I'll modify that as time goes along. And then you go to deformation processing if you want to follow through. From casting, you start out with the molten metal, you cast it into some shape, you then deform it, forge it, extrude it, draw it into some shape. You then might weld it, do NDT or other things. And so there's sort of a series of these, and I'm not sure I'm going to go too far over the years. I told Professor Hsu that, look, I got like 8 or 9 choices for students. The students could take the structural materials course 3 times and get different material, and I don't know why we need 12 or 15 lectures. I was going to do one on powder metallurgy. I decided not to do that. I was going to do one on coatings and vapor deposition, but Professor Thompson does something on that from the electronic materials point of view. So I think it's better to try to improve what I've been doing than create new modules. But you need to think about which of these modules might be of interest to you for your 3rd module. It looks like most of you are taking both of the live modules from Dr. Belmar and myself. But you need to think about that, and I'm going to talk more in the future about your presentation. And you'll have to think about that. That'll probably be coming up in October, beginning of November. The other thing is I talked to Adam Powell this morning, who's former faculty member of this department with a startup company, and he might come in and give a guest lecture. He's trying to develop new ways to refine rare earths. We talked about that for electromagnets. And he was telling me about the need for dysprosium. We talked about neodymium iron boron magnets. I didn't know about this until this morning. Apparently, if you replace 25% of the neodymium with dysprosium, you can get higher temperatures for your magnets. Right now, neodymium iron boron magnets hit their Curie temperature or whatever at about 80 or 90 degrees centigrade. And so you put that inside the engine compartment of a car in Arizona, and your magnet doesn't work because it gets too hot. And then, so they'd like to have higher temperature magnets, okay? And so the Department of Defense has put out a request for someone to sell them 1,000 pounds of dysprosium metal because they want to use it for magnets. Well, 1,000 pounds is only about $500,000, okay? Now, that's not a big enough market for most people. The Chinese apparently have put out something saying they're going to start producing 1,200 tons of dysprosium oxide, which is a fairly simple thing to go from the oxide to the metal, not that difficult. And so that's a whole different order of magnitude. The other thing, he's working on a process to make magnesium. And the automotive people always want to use magnesium because it's so light. And they would use more of it, but they don't have a reliable source for the volumes that they need. And that's what Dr. Powell's company is trying to do, is come up with a reliable source of magnesium for the automotive companies, a way to get dysprosium. And so he actually also has an economics degree from MIT. And so I've asked him, and he agreed that he will come in and give you a guest lecture about some of these externalities and stuff. I don't know which day it's going to be, but I told him it's got to be in the next 3 or 4 weeks because we're going to be done with the course in lecturing. Okay. Anybody have any questions from before? John, I got you your fracture toughness.
Yeah,
Okay. Yes.
I have a question about what you mean when you're saying we have to take extra modules.
Yeah, well, you're supposed to take 36 hours of lectures. So I'm giving 12 live, approximately. Dr. Belmar is giving 12. The other 12, you got to pick one of these modules, okay? I don't care which module you pick. You can't pick this one because that's what I'm doing right now. So that's off for this semester. Dr. Belmar's module is a different one than he's ever done before, so you could take either one of his before. If you were interested in structural life assessment that gets into fracture mechanics and stuff. If you were interested in extrusion and stuff, you ought to take my deformation processing one. If you're interested in casting, I don't care which one. Take your choice. And if anybody wanted to take this course again, you could pick 3 modules and take everything by video. And in fact, I have a student who's a senior who apparently did a summer internship in London, and they wanted him to stay until October 15th, so he emailed me. He's taking this course from London right now. Hey. And he'll show up to make a presentation to you. By the way, I think the class has gotten so large that I'm the only one who has to listen to all the presentations. So I may divide it up and only ask you to attend about half of them. I do want, the students want an audience. You know, you don't want to talk to an empty room of just me. So, but we'll come up with a schedule. And I'm not going to make all of you sit through 20-some presentations. I have to endure that. I mean, I have to do that. Actually, I enjoy the student presentations. I usually learn something. Because I think the students sort of get the hint that I like to go through a little bit of history of things. You ought to get that hint, because I do. And so they go through a history of things. I mean, the student who did the history of doorknobs, I mean, I had never studied the history of doorknobs before. And it's not something I probably would have done, but I enjoyed listening to it. Okay, any questions? Well, today what I'd like to do is talk about steel. No, actually steel and maybe then aluminum, but I want to talk about productivity through the ages, okay? And I handed out the other day, a couple of days ago, this thing, which is materials manufacturing, and it's sort of a history of nails, okay? And I want to go through that, but before I do that, this is the strength to density. I gotta do something about these things that are on the old overheads. Strength to density ratio of structural materials, and you start with wood and stone and bronze and cast iron and steel and aluminum and composites, and these fibers, and you see tremendous growth over time. Well, these are all different materials, but as structural materials, you know, the strength to density, this particular metric, if it's an important one to you, has increased dramatically. And I showed you the one for rare earth magnets. It's increased. I'm going to show you some other materials properties that have increased. Nails, as an example, or the making of iron, because we might talk about the ages of humankind. I handed out this thing at one time, this Ashby plot. You can talk about the ages of humankind in terms of the materials people used. Initially, they called it the Stone Age, right? So stone's in here, right here. And then they had the Bronze Age, a little bit later, 5,000 years later. And then they have iron right in here. But the Iron Age in general, you might start it in the 1400s. I'll read you something later that might say 1453 was the first iron foundry in Italy. And so we got into the Iron Age. We certainly got into the Iron Age after Henry Bessemer, and we got into, sometimes people call it the Steel Age rather than the cast iron. And then today, what's the age we're in today? Electronic material. Silicon, okay? So we actually named the ages of society after the materials. Historically, it was structural materials, but now we have electronic materials. But I wanted to talk to you about nails, simple nails. And I want to talk about the history of making steel, and the world's first energy crisis. And this comes out of a book from Penn State University Press called Out of the Fiery Furnace. This was a PBS series 25 years ago on sort of the history of metallurgy. And in the middle of this book, somewhere, they talk about the world's first energy crisis. Well, I don't know if it's the world's first energy crisis, but they call it the revolution of necessity, and the revolution they're talking about is the Industrial Revolution. But they actually begin in, they point out that the world's first, they talk about the population growth. In England and Wales between 1530 and 1690, the population nearly doubled from 3 million to 6 million people. Now, I may not see we got that many people, more than that in New York City right now. But when you have to transport fuel and water with 16th century technology, it's hard, okay? It's not even that easy today, but anyway. Over the same period, the city of London grew from 60,000 to more than 500,000, eightfold increase in 160 years. And that put a lot of strain on England. And it may have been the largest city in the world, but they don't know for sure because no one is keeping data in China of what was the largest city over there in the 16th century, okay? But one of the problems was, how do you get energy to all these people in all these homes when they start densifying in the cities? Now, this is actually a problem for today. Has anyone ever looked at the growth of megacities or the predicted growth of megacities in the world? A megacity is a city of more than 30 million people. And right now, I think there might be, in the whole metropolitan area, maybe New York and maybe Tokyo or New Delhi or something, or Beijing or something are approaching that. But they're predicting there could be 50 to 100 of these cities by 2050 as people keep migrating towards the cities, because that's where the better jobs are. And how do we know they're the better jobs? Anybody listen to the Oak Ridge Boys? Listen to country music? No, too old for you, okay, or too country for you. But they sing a song about the Depression, about the family that lost their farm during the Depression, and they moved to the city, and they bought and then Dad got a job with the TVA, and they bought a washing machine and then a Chevrolet. Okay, TVA and Chevrolet rhyme in that song. Okay, well, they got better jobs in the cities. And that's what's happening in China right now. People are moving from the rural areas to the cities. It's what happened in the United States in the 1790s. 97% of all the workforce was in agriculture in this country and most of the world. It was just an effort to grow food. And you didn't have time to play video games. That's why,
That's actually Alabama.
Was it Alabama? Well, I'll check. I'll check next time it comes up on my iPod, okay? Or my is it iPod? Yeah, it's an iPod. Anyway, so anybody know Alabama? Was it okay? No, but I mean, nobody else knows the Alabama folks. Anyway, maybe that. Okay. Anyway, it's a country music song. Maybe I'll bring it in. We can play it. Any case, I mean, the growth of cities is a problem, or is a concern, not necessarily a problem. But better jobs, when you don't need everybody out there growing wheat or rice, they tend to move to the cities because that's where the higher paying jobs are. As they move to the cities get overcrowded. And there are certain things that have allowed the growth of cities. Sometimes people will say that it was the development of the ability to roll I-beams by Bethlehem Steel in the 1890s that allowed the growth of New York City. Before that, you could never build a building over about 10 stories. Now, if you go to Otis Elevator, they will tell you that the growth of New York City was because whatever his name Otis was, developed an elevator. Who wants to walk 20 stories to get to work? Okay, or get down? I mean, there's no glory in having the top floor office if you got to walk up. Okay? Nowadays, the glory is to be on the top of a 100-story building, right? The highest rents are up there. Any case. So, what was happening in the 1500s, was they had a energy crisis. And it was actually the energy they were using before was wood. And the wood shortage was due to the growing demands of the iron-making industry, okay, according to these folks. The earliest water-powered blast furnace in Europe began operating in Italy in 1463. And they found that cannons could be cast from iron instead of bronze. Okay, bronze was expensive. Cost comes in again. And they could make, their military industrial complex could make cannons out of cast iron, but to make iron you needed charcoal. And to get charcoal you needed wood. And so they called the Weld of Kent, W-A-L-D, was where all the mature oaks, beech, and chestnut, beautiful forest, and they were cutting them down to make charcoal. At the time, there was a competing industry, warships, again, the defense business. It took 2,100 tons of wood to build the HMS Victory, which was Nelson's flagship at Trafalgar and stuff. But these ships that were allowing the countries to wield their power around the globe, now that they knew the globe was round, took a whole forest to build one ship, okay? And in fact, we still have that problem. The best wood, if you looked on those Ashby type plots and it has wood on there, anybody know what Old Ironsides is made out of? What type of wood?
Red oak.
Red oak. It's actually white oak from North Carolina. But, no, close. But white oak, actually it's live, I think it's live white oak. Anyway, there's a shortage of it in the world today, okay? But it tends to, the strongest wood in the world, and the reason it's called Old Ironsides is it was made out of this oak from North Carolina, whether it's red or white or live or whatever, yes?
I was camping in Maine one summer, and they were talking a lot about the white pines up there, the really tall, really short,
Yep.
which they used for maps up there. Apparently it was illegal to cut down those because they were the king's wood.
Right.
When it was
I'm going to read you more about that from England. But yes, they would put royal decrees on the forest. In that case, they wanted these nice straight pines, but that wasn't the strongest wood to defeat cannonballs on the sides of the ship. So the ship is made with different, you selected different woods back in those days for different applications. But turns out they just did a repair on Old Ironsides, and they were having a problem getting the oak from North Carolina. They just did a repair on down here in Plymouth on the, the Mayflower 2, and it was like 2 years delayed because they couldn't get the oak from North Carolina. It turns out one Navy officer was in my office a week ago, and he was telling me that the minesweepers are made with this same oak from North Carolina, okay? Because it's the strongest wood, best for certain types of shipbuilding. In any case, yeah, they're made out of wood because you don't want anything that's metal. Okay, and the fuses on the mines in the ocean work off sensing that there's something metallic around, right? So they have to make them out of wood. Okay. So the two uses of oak, basically building ships and making iron, were in conflict, and now a third industry added to the demands, and it's called glassmaking. Okay. In 1558, a law was passed forbidding the felling of trees to make coals for the burning of iron, but as good politicians, the Weld of Kent and Sussex was exempted. So you couldn't cut trees for making iron by royal decree, except where they were making iron. Okay, so even the lobbyists worked back in 1558. Okay, but one writer complained in London that the price of wood had gone from a penny to 2 shillings. I was going to look that up this morning. I don't know what I think a shilling is. I can't remember how many pence in a shillings, but someone can look that up. But that's a big increase in price. By 1581, the lobbyists had lost, and the shortage of wood for shipbuilding was so serious, so this is your white pines from Maine, was so serious that a further act was passed forbidding the felling of trees within 22 miles of the Thames River, within 4 miles of the great forests of the Weld, and within 3 miles of the coastline anywhere. You had to move these big tall trees to wherever you're going to build them on the coast, right? By 1615, England was facing an energy crisis. A royal proclamation of that year lamented the disappearance of the kind of wood which is not only great and large in height and bulk, but hath also that toughness of heart, as it is not subject to rive or cleave, and therefore of excellent use for shipping. So we get into fracture mechanics here too. Okay, except they didn't know about fracture mechanics back then. Well, in any case, what I wanted to talk to you about is making of nails and how that all fits together. I've estimated that the productivity of making steel, and it's in this little materials manufacturing thing that I handed out to you. This is a Tom Eager estimate. That it took in the early 1600s about 1 person year per ton of cast iron that was produced. You had to go out there and cut down a few tons of cordwood. You had to then turn that into charcoal. Do you know how to make charcoal? Anybody know how to make charcoal? How do you make charcoal?
And make a big pile of wood and then burn a layer on top of it to oxidize it, or to not oxidize it with no oxygen. So it's still
Yeah, exactly. I don't know how well this is going to show up. It's out of the fire, well, out of the fiery furnace. But basically, you lay a bunch of cordwood. Here's a guy, can't really see him very well, shoveling. But you lay down the cordwood. You then might even cover it with dirt, just pile dirt on it, and then you put some straw or something above that, and you light it on fire. But there's not enough oxygen, and so all you're doing is it's a slow burn. The whole thing heats up, and it vaporizes off the lignin in the wood, and that burns off and leaves charcoal behind. Okay, which is mostly coal. And why do you want charcoal? Because charcoal burns cleanly. Okay. There are some types of coal that burn very cleanly. This I stole from the blacksmith forge downstairs. This is a piece of anthracite coal, which there's not that much anthracite coal, but the anthracite in the world compared to all the other coal. But the anthracite coal is, it's been cooked in the earth under pressure and heat for millennia, and then we go dig it out of the ground, and it's got most of those volatiles burned off. Now, most of the coal that we burn in a power plant is what we call bituminous coal, which has not been cooked as long and it has a lot more volatiles in it, or even subbituminous coal, which is sometimes called lignite, and it's old plant fibers that have not been cooked very long. And you can buy that stuff out of Colorado or Wyoming at $5 a ton today, okay? It costs you more to ship it out of Wyoming than it does to dig it out of Wyoming, okay? So coal is pretty cheap there. In West Virginia, the better quality coal might cost $40 or $50 a ton. I also have a piece of shale here. If you want to look on the edge of the shale, you can actually see some of the layers, which I believe are oil. So if you want to know about fracking, and that's basically shale in the ground, is got a bunch of, it's porous and it's got hydrocarbons in it, whether it's gas or oil. In any case, what happened is they were having a shortage of wood. The revolution of necessity that this book talks about is basically the fact they had to start using coal because they couldn't use wood. And they would first go along just along the ocean, and you could pick up what they called sea coal. So wherever the waves had come up against some coal seam, you'd have sea coal on the beaches. Well, once they'd removed all the sea coal trash from the beaches, they had to start digging for it. And when they had to start digging for it, they had water in the mines, and they had to develop steam engines to pump the water out of the mines. And then they had to worry about, were they spending more money running the steam engine pumps than they were getting coal out of the mine? I mean, this is a question of economics here. And it turns out that ended up leading to, believe it or not, the science of thermodynamics. Okay? And James Watt and steam engines and things like that. So the science came out of the revolution of necessity. If you wanted to have iron to build hinges or nails or build cannons for warships, if you wanted to have wood for other applications, or if you wanted to have something so you could make glass, which you need a clean fuel to make glass. You have to have something that burns cleanly. Why? Does anybody know why you need a clean burning fuel to make glass? Purities, yeah. If you have a sooty fuel, it'll get in the glass, and your glass is no longer going to be clear. It's going to be full of carbon dust, and it's not clear. And you're making glass as a clear material. So they decided to build in the New World some of those things, because we had over here, we had forests still. The Indians had not cut them all down. And so the British came over to cut them all down. And they built in New England in the 1630s something called the Saugus Iron Works. Anyone ever been to Saugus to see the ironworks? Go up to Saugus right up here. I mean, you don't want to walk it, but it's only about 20 minutes away. And they have the Saugus Iron Works. They built a blast furnace. Why? Because we had wood. We were solving the energy crisis for Britain. They could make iron and ship it over there, and the foundries over there could make cannons or whatever, but we had the energy source here, namely wood. Anyone ever been to Jamestown, Virginia? Yeah, so they had an industrial plant there. Okay, you don't remember. Oh, I haven't been there for 35 years. You've been there more recently than me. Okay, but in any case, they built a glass furnace in Jamestown, which 35 years ago, you go and watch them make glass. So in any case, again, there were trees in Virginia. They were running out of trees by royal decree in England. How did they make nails going back thousands of years ago? Well, it turns out I have a little history here of cut nails in America. This is cut nails, but it says that nails date back to 300 BC, and they have excavations of sunken ships from 500 AD showing nails. And back then, people used to forge the nails. And in the winter, when they didn't have crops to grow and harvest, I told you that 97% of the workforce in 1790 was in agriculture, and now it's less than 3%, and that's why they can move to the cities. But back in the old days, if you didn't have anything to do in the winter, you might just sit there and forge nails. And it turns out a 10 penny weight nail was the size nail that you could get 10 pennies for 100 nails. And an 8 penny nail was a smaller nail. It only cost 8 pennies anyway. But they were hand forged from before the Christian era to, the 1600s. They were forging individual nails. Okay? They would burn down barns or houses and sift through the ashes to recover the nails, because it was about 1 person year per ton to produce this. And what's the productivity today? Well, the productivity today to make nails or steel is about 20 minutes per person ton. Okay? Now that's a pretty high increase in productivity. And as a result, you can buy a ton of steel today, if you just want to buy garden variety steel, for $400 or $500 a ton. Okay? The equivalent price back in 1600s, nails were a valuable commodity, as were hinges or anything else. And so if you want to learn more about nails, you can go to it's supposed to be Tremont Nail Company. It's right down here in Weymouth, Massachusetts or something. But they've been making nails for almost 200 years. They misspelled it on their name on the top of their thing. But anyway, see at the top it says Tremont Nail Company, but the title in blue is misspelled. But, from 1819, who knows how to spell. But anyway, it tells you a little bit if you want to read about nail making. So far as glass, and to show you how materials change in their value, just like nails have changed in value. Oh, and I have some nails from today. See, I have little touchy-feelies. So, oops. There's my spiral nail. So this one's got a spiral to it. It's got a head on it. I passed around the cut nails. Cut nails replaced forged nails in around 1800. Here's a regular old nail, but this one's coated. It's got some rosin or stuff on it so it grabs to the wood. And here's a little nail. okay? Just a galvanized nail. So you can look at nails. But another industry was to make glass, and they still have glass blowing. If you go look up sugar hollow glass, I think some of these references are on the handout I gave you. But if you look at sugar hollow glass, or if you go to Jamestown, they will show you how they made glass for window panes. And they start out just like they do. You can go to the basement of building 4 here and watch them do a glass blowing. They get a blob of hot glass on a steel tube. They blow through it to make a bubble of glass. They then start spinning it and taking steel tools and forming it, and they spin it into a big flat, and that big flat, they can cut out little panes of glass. And those little panes of glass came in 2 forms. Sugar hollow glasses, I don't know, they're in New Fairfield, Connecticut, and they will sell you bullseye glass. Anybody ever seen bullseye glass? This is the center of that little tube, and it's got a blob of glass on it, because where they cut it off, you have this sort of sharp blob in the center. This was the junk in 1600s, was bullseye glass that was not taxed. Remember taxation without representation and all that stuff? Okay, and people would put it over their door to let some light in so they wouldn't have to burn as many candles. And it wasn't taxed, and so this was the junk. All the good flat stuff went into the churches or the rich folks' homes and didn't have this big blob and didn't distort the view. Just let the light in at the top of the door. So back in the old days, the bullseye glass, which was the center of this spun piece of glass, was the junk, and you would pay extra for the somewhat flat glass that was, went into windows like this. By the way, if some of these at MIT from 1917 are original, I don't know how many are still original, you actually can see by looking carefully they're not completely flat, because the way we made glass in 1900, companies like Pittsburgh Plate Glass, they would take the glass as a big sheet off a big mill, and they would have a mill that ran for half a mile to a mile, just straight down, and they would polish the glass to make it flat. But it was sort of wavy as the glass cooled, and you had to anneal it and so it wouldn't shatter and stuff. But then someone, Pilkington in England, I don't know, 1920s or so, came up with something called the float glass process, where you'd pull that glass off when it was hot, and you'd float it on molten tin, which is perfectly flat because of the Earth's gravity. And the top surface is also flat just because of surface tension. And you could eliminate all that half mile of polishing. So now you only have like 100,000 yards, I'm not 100 yards of annealing on this float glass product. And so newer glass is all float glass and got rid of all the polishing. But in any case, in the old days, the cheap glass was the bullseye glass. Now you can pay a premium to get bullseye glass from Sugar Hollow Glass, and pay a big premium because it shows that your house looks old, even if it was built 3 years ago. Okay? So don't ask me the economics and the emotions of different people, why in the old days they wanted, well, I can tell you that in the old days they wanted bullseye glass because it was cheap. Nowadays they want bullseye glass because it looks old, even if it isn't. But then they buy cosmetics so they don't look old, and never mind. Anyway, so there's a revolution of necessity. But nails, the history of nails is, I've kind of gone through that. We've talked about the revolution of necessity. If I look at steel making more recently than going back 400 years ago, starting in 1925, it was about 50 or 60 pounds per person hour. So it'd take 40 or 50 hours worth of labor to make 1 ton of steel in 1925. And this is going up to about 1980. It was getting to the point of 6 hours a ton about 1980. And what happened in 1980 Well, in 1980, we had our second energy crisis of the modern era. 72 was the first oil embargo. And then they had an energy crisis around 78 or 79. And it turns out this is the production of steel in the 1980s in the United States. Millions of metric tons. And if you just sort of ignore these little variations in here from 80 down to 56, this is the 82 recession. But the production of steel in the United States was constant along this blue line, more or less, right? At about 75 million tons, except for depressions and things like that occurred, those externalities. And the actual use was about 100 million tons. Now, what happened? There was also some big changes in the industry. They used to make steel, and you'll find this when I talk about casting, by pouring it into an ingot mold. And then in the 1960s, some people, Alpine I think it was, in Austria, decided to see if they could continuously cast steel. People have been continuously casting gold and silver and copper and things like that for several decades. But steel melts at a higher temperature, and Voest-Alpine decided in the 50s and 60s to try to develop a continuous caster for steel. Much bigger market. And in the 60s, they actually would sell you a unit. But it turns out the people who were the rocket scientists, as I used to call them, who were hired into the steel industry after World War II. Remember I told you, after World War II, the United States had bombed out all the competition. That's one of those externalities. And we had 75% of the world's steel market. In the mid-60s, when these guys were the middle-level managers, they and the upper managers decided not to put in continuous casting in most U.S. steel mills when they were building a new casting shop. The guy who later became the head of Harvard Business School, the dean of Harvard Business School, was telling me in the 1970s how this was the right decision. I'm sitting there, Kim, you're explaining to me as a metallurgist this stupid idea was the right decision, because the business managers can justify, they can rationalize stupidity. The difference between an ingot mold of making steel and continuous casting is something called yield. So if I've got an ingot mold to make steel, I'm going to pour it into this mold. It's got sloping, it's a piece of cast iron, great big piece, maybe weighs 30 tons of cast iron, and it's got sloping walls, so when it cools and contracts I can turn it over or pull it out without sticking to the walls. And I cast the steel, it starts out and I pour it in that level, but as it shrinks, as it solidifies, I get what we call a pipe, and when I'm all done and it's solidified, I got to cut off 1/3 of the top and send it back to remelt it. As a result, my yield when I was at Bethlehem Steel in the mid-80s was about 67% of tons poured versus tons shipped. Okay, and we called that the yield. And there was a guy, graduate of MIT, metallurgist, Mike Harashimchuk was his name, and he was responsible for Bethlehem Steel's yield. If he could get the yield up by 1%, our profits would double. Okay? So it was his job to figure out how to improve the productivity of casting. If you do a continuous caster, which is a machine that's about 10 stories tall and cost $100 or $200 million back then, you basically would have a mold, a vibrating copper mold up here, water-cooled copper. You'd pour the steel in, and your shrinkage would be right here, but it would shrink down along the sides, and then you would bend the steel on the lower 8 stories, a hot beam of steel, and it comes out, I'll show you a picture of it in a second, as a continuous caster. You don't have to cut off the top because you can continuous cast. Nippon Steel's continuous cast for like a year without shutting down. 24 hours a day. Just keep pouring more steel in, and now your yield goes to 95%. Okay? What happens to your profitability? So what happened to the U.S. steel industry? In 1968, when Armco Steel put in new casting facilities, and they could have put in a continuous caster, what did they put in? Ingot casting, because there was no risk. Okay? What do you mean there's no risk? The Japanese were putting in continuous casters, and they were beating your socks off with productivity. You went from 6 hours a ton to, they went from 6 hours a ton to 1.5 hours a ton because of the productivity increase of using continuous casting. When Bethlehem Steel built the world's last steel mill built by a company in the 1960s, from 65 through 70, took them about 5 years to build it. It's probably about a $5 or $6 billion investment. Just about bankrupt the largest company, the second largest steel company in the world, Bethlehem Steel. They put in ingot casters. Okay, and both these companies in the mid-70s took out their ingot casters and put in continuous casters at a cost of a few $100 million, okay? Because all of a sudden they realized what they should have known 10 years before, that continuous casting was the way to go. And so today, 98% of all the steel in the world is continuously cast. You can buy continuous casters that are only 4 or 5 stories tall for what we call mini mills that don't put out 10 million tons of steel a year in one mill. They put out 2 million tons of steel a year. Okay, much lower capital cost and whatnot. But anyway, there's a problem in the industry in 1980. By 1980, you have this continuous casting coming online. And continuous casting is basically changing the entire economics of the steel industry. It's also cutting jobs by a factor of 2, because if you have usage or tons poured staying constant for 10 years, but you have productivity going up by a factor of 2 from pounds per man hour back here at 150 up to nearly 300, so the productivity goes up by a factor of 2, but consumption stays constant. What happens to employment? It drops from 500,000 down to 250,000. So all the pundits on Wall Street and in Washington say, oh, the American steel industry is defunct. They're just dying. They were, okay, economically they were dying, but not because they couldn't compete. They had doubled their productivity in 10 years. There's only one industry that had improved their productivity better than the metals industry in the 1980s. Anybody know what it is?
Oil?
No. Well, close to oil. Mining. The mining industry had the manufacturing industry in the United States in the 1980s had a 4% annual productivity gain. The mining industry had a 6% productivity gain. And the lesson from all of this, the threat of extinction sharpens the mind and allows you to take bigger risk. When you're going to go out of business anyway, you will take bigger risk. In the 1960s, the steel industry managers were not willing to take any risk. They were going to put in the same old thing they've been using for 80 years, okay? When they were faced with, if we don't put in something that increases our yield from 67% to 95%, we're going to be out of business. They'll take the risk and they'll make it work, okay? There's some great stories about making it work, taking the risk and making it work. In the electronics manufacturing sector, in the 1990, it was well known that you had to have 4% rework on all your printed circuit boards. If you built a printed circuit board plant anywhere in the world, you would have a repair area that could handle 4% repairs to the printed circuit boards. It's a valuable board when you finished it, right? And if it doesn't work when you burn it in, you go in there and figure out what it is and have someone resolder, whatnot, and then repair it. This Motorola manager in Boynton Beach, Florida, had decided, nope, we're bringing back the production from Singapore to Boynton Beach, and we're going to use these, minimum wage American unskilled labor, and we will design our plant for zero rework. We are going to allow nothing to be reworked. If it doesn't work, we're going to throw it in the scrap bin. Okay? And guess what the process engineers achieved at Boynton Beach? Near zero rework. Because they went and fixed the process so they didn't make defective product in the beginning. And all of a sudden, this rule of thumb of you need 4% rework, that was a self-fulfilling prophecy. If you put in 4% rework, the engineers would improve the process until you got to where the rework area could handle the amount of rework. And you wouldn't keep on improving the process. So it was a self-fulfilling prophecy. You don't believe that? You think that's an isolated story? Ford Mustang plant, okay? $1 billion facility, turning out one vehicle a minute off the end of the assembly line. This is around probably 1994, 1995. So, oh no, this might have been the 1980s. Anyway, so I get a tour. We're doing some work for Ford, and the guy says, let me take you over to the Mustang plant. And he took me to the end of the line. He says, it used to be that when you got to the end of the line, they'd fill it with gasoline, you'd turn the key, and the guy was supposed to drive it into the parking lot to be loaded onto the trains to be shipped around the country. And if it didn't start, you had one of the tow motors, one of the forklift trucks, come and pull it out to the repair area so some mechanic could go out there and figure out how to get it started and working. And then you'll buy this semi-defective car because it finally got working. New manager. The new manager says, no more tow motors. If it doesn't start, you push 100 to 150 yards to the parking lot. Guess what? Within a couple of months, they were all starting at the end of the assembly line. Why? Because those guys who had to push it went to those engineers and said, fix it, okay? And they did. So this is a lesson in management of manufacturing, okay? And improving productivity, okay? So I've taken you from 1 person hour per ton, one person year per ton in making of steel to the modern age of about, what did we get to in 1990? We were at sort of 3 or 4 person hours per ton, or 6 or something like that. Well, then the mini mills came along in 1975, and some of these guys learned that you could buy scrap steel on the world market for $100 a ton. You could make cast iron from virgin ore for $180 a ton. And they said, I like that idea of $80 a ton excess profit by just melting old steel rather than taking virgin ore. I'm going to build an electric furnace plant. And one of the guys who did this, a guy named Gordon Ford, a graduate of this department. Nucor Steel is the one who made it the biggest. And they made what they called mini mills. Instead of a $5 billion investment by Bethlehem Steel in the late 1960s, no one else in the world had ever built, since Bethlehem Steel, no other country, no other company has ever built an integrated steel plant. The current cost of an integrated steel plant would be $15 to $20 billion to build a plant that could turn out 10 million tons of steel. And remember, we're producing 1 billion tons of steel a year, so 10 million tons is just, you need 100 of those plants around the world. But they built a lot of new plants. The thing is, they're no longer built by companies. Bethlehem Steel almost went bankrupt. They're built by countries today. Korea decided in 1972, just after Bethlehem Steel, President Park took Colonel Park, his chief of staff, and said, you're in charge of POSCO Steel, our new steel company. And the government of Korea teamed up with U.S. Steel and built POSCO Steel. And 30 years later, they surpassed Nippon Steel as the world's largest steel company in the 1990s. Okay? What happened after that? The Chinese started making lots of steel. And Bao Steel, BAO, is the world's largest steel company today. Okay? Countries build steel plants. But it's the same in other industries. It's the same thing in the aerospace industry. There's only 2 competitors, Airbus and Boeing. Neither one of them can afford the $10 or $20 billion investment to build a new jetliner like the Dreamliner. So they get all kinds of government subsidies, and the politicians on both sides of the Atlantic argue that you're giving unfair competition advantage to your aircraft industry, okay? But they are, okay? They're doing it, but there's only 2 companies there. Same thing happens in semiconductors. You want to build a new super super submicron size semiconductor fab, 10 or 20 billion dollars. Intel probably built the last one, but now they're parsing and breaking up the industry in different ways, so no company today has the profitability in semiconductors to build a $10 billion fab. We are getting to economies of productivity and scale that really require national investments. Sometimes outright, like POSCO Steel, or 20 other steel companies that have been built in the last 40 years, built by countries, or in the case of aircraft, just pure government collusion, okay? And just fighting among the politicians on both sides of the Atlantic. Or in the semiconductor business, they sort of restructured things and partnering, and they worked out different things because of these huge investments to get levels of productivity and increases in productivity. Today, steel takes about 20 minutes a ton compared to 1 person year, 3,000 hours 400 years ago. But the change as when you were, well, I guess I can't say when you were born. Most of you are too young for that. In the 1980s, when your older siblings were born, steel was 6 hours a ton. Well, in 25 years, we've gone from 6 hours a ton to 1/3 of an hour a ton. That's an 18-fold increase in productivity. And everybody says